Hey everyone, welcome to a new video. So in this video, we'll be learning how to perform a finite element analysis on a uniformly loaded cantilever beam using SolidWorks. So to begin with, let's open SolidWorks, click on the part modeling and click on the sketch module here. Select the sketch, choose the front plane and draw a rectangle. Dimension it as 0.03 and 0.03 on either sides, that is it's a square. Now click on the features here, extrude the sketch to a distance of 0.5 meter, click OK. So this is the beam that we are going to use for our simulation. Now that we have drawn the part, click on the simulation and select new study. So we are going to perform static structural analysis on this beam. Select the static analysis and click OK. Right click on the part, click apply material and select the alloy steel, click apply. Now close the window. So first we are going to perform a 3D analysis on this beam. So let's go ahead, define the fixtures. Since this is a cantilever beam, let's fix one side of the beam and click OK. Now to apply a uniform load on this face, right click on the external loads, select force, select the face you want to apply it on and input a value of 1000 newtons, click OK. Now that we have defined the boundary conditions and the loads, right click on the mesh and click create mesh. Here you can use either the default option to slide over between the coarse and the fine mesh, or else you can click on this mesh parameters and manually import a value for the mesh that you need. In our case, let's use a 6 mm mesh, click OK. You can see the model has been meshed and the mesh is looking fine. So let's go ahead, run the simulation. You can hit this run this study option or click on this mesh and select mesh and run. So this is a pretty simple and straightforward simulation, hence it took very less time. So you can see we have the stress plot, the displacement and the strain plot for the beam. So we are looking at 1 major stress here. So the maximum value of 1 major stress is 5.8 e power 7 Newton per meter square. And if you look at the displacement, so right click on this, click on animate to view the animation of the simulation. You can even save this as a AVI file, but we are not interested in doing that now. Right click, and if you want to look all the plots in the same window, right click on the results, click compare results and click OK. So here you have the model along with the loads and constraints. We have the 1 major stress in this window and we have the displacement here and the strain is being plotted in this window. We have successfully completed a 3D finite element analysis over a cantilever beam. Now let's consider this same part as a 1D model and look at the results. So to do that, click on the model and hit the simulation button, hit new study, rename the simulation setup as 1D static. Now since it's a 1D analysis, we are going to consider this whole geometry as a single beam element instead of discretizing it into small elements. So to do that, right click on the part. So first apply the required material. So right click on the solid part again and select treat as beam. So in our case, since the length to width ratio is very large, our part was directly considered as a beam. But if your length is not proportionately long with your width, you may get a warning saying the slenderness ratio is not large enough to treat it as a beam. Now that we are good to go, let's go ahead and define the boundary condition and loads for this 1D FEA. Right click on fixtures, select fixed geometry, select this joint and click OK. Now to define the force, right click, select the force, select the whole beam, and for the application direction, select the face it's going to be a downward force of 1000 Newton. Click OK. Now right click on the mesh, create mesh. So after meshing the geometry, the 1D representation of our 3D model is shown in the screen. Now let's go ahead and run the simulation, and there you go, you have got the results instantaneously. Similarly, we can go edit the chart options and change it to floating, go to definitions, change the units to Newton per meter square, millimeter square, sorry, and now the results looking meaningful. For the displacements, let's go ahead, change the settings, and the chart options should be floating, and okay. Yes, so apart from the standard stress and displacement results, since we have considered this whole part as a beam, we can request for beam bending moment and shear stress diagram for this particular beam. First, let's look at the shear force diagram. We have successfully completed the 1D FEA analysis too. Now finally, if you want to analyze the same beam as a 2D shell element, we can do so by clicking on the model, choose a new study, select static and rename it as 2D static. Now since it's a 2D element, we are going to consider this whole beam as a shell element. Before you do that, apply the material and right click on the path model, define shell by selected face. So we are going to consider this whole beam as one shell element with a thickness of 30 mm. Yes, and click OK. So now to define the fixtures, right click and select fixed geometry, and since we have converted this whole solid part into a shell element using this face, we need to define all our loads and constraints to this particular shell. Click on this edge and select OK, and right click on the loads, click on the force. Now to apply the force, select the face on which this is going to act, and let's select the direction. So it's going to act in the downward direction with a force of 1000 Newton. Click OK. Now right click on the mesh, create mesh. Here you will be provided options to vary the mesh parameters. Since it's a shell element, we can use 6 mm mesh. So this is the 2D representation of our solid part, which will be used for the analysis. Now let's go ahead and run the simulation. So we have received the results from the simulation. So let's go ahead and define the legends properly. Click on settings and chart options, floating definition should be Newton per millimeter square. Yes. Now for the displacement, it's again going to be settings, chart definition, floating. Yeah, sorry. Right click and show, and then right click on settings, chart options, floating. Yes. So we have successfully completed a 1D, 2D and a 3D FEA analysis for a uniformly loaded cantilever beam. So to view the results of all the three types of analysis, click on this result options and compare results, all studies in this configuration. Let me look at the displacement results alone for all three. 1D, 2D and yes. So let's select OK. Yes, and yes, so this is the model that we use for our analysis, and we have the 3D simulation results here, the 1D results and the 2D results. If you look at the values, we seem to have received approximately the same values in all three simulations. So depending upon your requirements, you may choose whether you want to perform a 3D analysis or a 2D analysis for a particular part. For example, if you have a part in which you have lengthy members and you are only concerned about the bending stresses in that lengthy members, then you can very well consider the member as a 2D element or a 1D element to avoid computational complications. So instead of going for a 3D model wherein you have a lot of elements, you can consider it as a 2D shell element or even a 1D element and look at the displacements and the stresses developed. Okay, that being said, let's first save our simulation setup. File, save. So let me save it in the PC using a new program. New folder, SolidWorks Simulation. So we have successfully saved the simulation, and now let's learn how to perform a parametric study using SolidWorks simulation. So to do that, so right click on any simulation. So in this case I'm going to perform a parametric 3D analysis. So I'm going to select 3D static and then create a new design study. Once you do that, a complete new window will open up with your model and dialog box with various options like variables, constants and goals. If you just uncheck the optimization, you won't be able to access the goals, but I'll teach you how to use this optimization option. So what's the use of this parametric design study in SolidWorks? So why do we need it? Let's consider a case in which I want to increase the length of this member and change the material, or even try to change the width of this material. I need to go back to the modeling again, remodel my part and check if the stresses are below the required value. So instead of doing all this all over again, so in SolidWorks you can, in the variables, you can select the parameters that you need to vary and even input the ranges between which the values change, and in the constraints you can add a limit. For example, I can conduct several simulations and look at results which have a maximum factor of safety value as 2. And finally, in the goals, you can choose to minimize or maximize certain values. All this will make sense once we perform an example study. So let's go ahead and choose the parameters that we want to vary. So once you click the variables and add parameter, a dialog box is going to open up. So here, let's rename it as length. And for this length, it's going to be from the model dimensions. I'm going to choose the length here. So that is one parameter that I want to vary. The other one is going to be the width, and I'm going to choose this, yes. And next, apart from varying the length of the part, you might as well play with the mesh size. So to do that, click on this drop down menu. We're going to get this value from the simulation. Go to the analysis, select the mesh, and once you do that, there will be several parameters that will be listed, and from that you can choose which one you want to vary. I'm going to vary the global size, and I'm going to initially start with a 6 mm mesh. Make sure the units are right, or else your simulation may end up with errors. Now you can even control the force value as a parameter. So click on the simulation, select the force, and I'm going to use 1000 newtons initially. That's it. Click OK. Now you can see all the variables have been added to this list. I'm going to vary the length, the force that is applied, mesh size, width. And for a better view, click on the table view here. Before you do that, make sure all the ranges make sense. My minimum length is going to be 0.5 and my maximum length is going to be 1 meter. Maybe, yeah, I'll go for 2 meter. The force ranges from 1000 newtons to 10,000, and the step is going to be 2000. For this, I'm going to step by 0.5 meter. My minimum mesh size is going to be, I'm going to use a 4 mm minimum mesh size and a maximum of 6 mm. the step is going to be 2 mm. For the width, the minimum width is going to be 0.03 and the maximum is going to be 0.09. The step is going to be 0.03. So here you would have noticed that I am going to vary the mesh size, and this is what we call as a grid dependency test in FEA. That is, so you will be asked to perform the same simulation for different mesh values and look at the variation results. So once you perform several simulations for different values of the mesh, you will notice that after a certain refinement, the value of the output results will not change. So that's the value that you can rely upon from a FE analysis. So SolidWorks parametric design study is very useful while performing such grid dependency tests. Yeah, now that we have populated this table, and let's define the constraints. Click on add sensor. I'm going to say that the factor of safety shouldn't be less than, it should be greater than 3. So that's my constraint, and I'm going to add another constraint saying that from the simulation data my stress values shouldn't go above 6G. Yes, so it should be less than 6G, and the minimum factor of safety should be greater than 3. Since the optimization check is on, I am allowed to add a goal. So my ultimate aim is arrive at an optimum value for designing this beam with the minimum mass. So let me select this mass, and I'm going to minimize the mass. Okay, so I hope we have defined all the variables properly, and you can see that total active scenarios are 144. What do you mean by 144 is we have 144 simulations to run, and after running all this simulation, SolidWorks is going to pick the best value for you. It's going to pick the best or the optimum value for you and show it to you. So to run this parametric design study, click on the run button here. Wait for the solver to finish all 146 design scenarios. This is going to take considerably long time, and you can see how much time we have saved using this parametric design study. Imagine what would have happened if you are going to manually set up the simulation for each cases and look at the variations. So this is a great tool to use while you are performing parametric study. Okay, SolidWorks has completed 3 scenarios, and all 3 have failed our requirements. You can see in the GUI the model is being continuously changed as per the values we have given, as per the range of values we have given. So let's wait until all the simulations are done and look at the results. So as you can see, our target stress was 60 Newton per millimeter square, but seems like the value was not imported properly. I'm going to go back to the variable view, change this to 60 Newton per millimeter square. And click run. So let's wait again. So the stress is going to be less than 100. It's rough. So make sure the rest are same. So since we have more than 100 case scenarios, I'm going to reduce the range between these values change. So let's say this is 0.5 to 1.5, and I have a step of 1 meter, 1000 to 5000, step of, let's say, so 1000 to 6000, and step of 222, so 3, 5 and 7. Yes, so let's say we have a step of 2000, and for the mesh it's going to be, yes, for the width I'm going to have maximum of 0.06, step is going to be 0.3, and you can see now Now we have considerably reduced the number of design scenarios. So let's run the simulation again. This time it is definitely going to take less time, and we can look at the output results. Okay. Huh? So this concludes the video. Thanks for watching. You will be given a challenge to attempt on. I'll see you guys in the next video. Bye.